Okay, so today I'll start Kuga's book. We will start with so-called free groups. So that will be something very fundamental in the study of fundamental group of a topological space. First, let's remember what is a group. A group G is a non-empty set with an operation on it, right? Which maps a pair of elements to so-called their product, satisfying the following properties. This operation is assumed to be associative. Okay, so x times y times z is x times y times z, associative. There is an identity element. Such that e times x on x times e is equal to e for all x in G. So there is an identity element, and there is a inverse element. So for any x, there is some x inverse in G, so that x times x inverse and x inverse times x is equal to x. So any set with an operation satisfying these three conditions is called a group. This is something we know from maybe even high school, right? High school'da görüyor musunuz bunları? Bizim zamanımızda görülüyordu, değil mi? Okay. What about free group? I will not give all the details about free groups. You know, there are lots of details, and if you want to do it properly, but you know, this is not an algebra course, so I will not go all the details. The free group on a set A consists of words with letters letters are elements of A. Okay. An example. So let's say A is the set X, Y, Z. So this is our alphabet. You write words using these letters. For example, X is a word, X times Y is a word, Y times X is another word, X times Y times Z is another word. And we will also use inverse notation. So these are also words, and so on. Okay. And we will also, you know, use this kind of notation. So x cube will correspond to actually the word XXX. Okay. So these are the elements of the free group. Identity element is the empty word. So this is the empty word. So no word, okay? So that's the identity element. And product of two words. Two words. Well, you just put two words together. For example, if this is a word and this is another word, how do we define the product? Well, you just drop the parentheses and write the word by just obtained by just putting one next to the other one, obeying this, of course, order. Okay, this is the first word, this is the second word, so I just put them like this. So this will be the product operation, and we will also write, you know, x times x inverse. So this is the identity element. Sometimes I'll write e, or sometimes I'll write just, you know, so this is the empty word. This will be the empty word. In other words, you will just, you know, whenever you have this, you will just erase it. For example, if you have something like this, let's say, x, so we will have this, and so we have z times z inverse. That's the identity element. That's the empty word. So I'll just, you know, erase them. You know, instead of this, I write nothing. So they just disappear, and this is the result. Okay. So that's the cancellation property. And we should keep in mind that x times y is not y times x, right? They are different words, so they will be considered as different objects. Therefore, a free group on a set with more than one elements is not abelian. Okay. If you have, of course, just one letter, then it will be abelian, but otherwise it will not be abelian. Okay. Of course, you know, one has to actually prove that, you know, such a thing is really a group, right? This is a well-defined object and so on, but we will not go into those details, okay? So there are lots of things actually that needs to be proved here, but we will ignore them. I'll just mention the following property that's kind of a universal property for free groups. What's that? So we will make use of this proposition. Let F be a free group on an alphabet A X alpha in some index set. So this alphabet doesn't have to be a finite set, okay? It can be a set of any cardinality, and G be any group. For each alpha in the index set, choose some G alpha from the group. Okay. Diyelim ki G grubundan her alfa için bir tane eleman seçtik. Conclusion şu o zaman. Then there is a unique group homomorphism phi from F to G, so that image of X alpha is just G alpha for every alpha in the index set. So this is like, basis of a vector space. Once you define the image of basis elements, then there is a unique homomorphism from your vector space to any other vector space. So this is just the group theoretic version of that, in a sense. So a free group has this property, and actually this is kind of the universal property of free groups. One can show that actually there is a free group for every alphabet, and actually up to isomorphism it is unique. So this property makes it actually unique. So for every alphabet up to isomorphism there is a unique free group. Efendim? Şöyle, A bizim alfabemiz, bunlar letter'lar, F free group, yani word'ler. Yani her bir letter'ın nereye gittiğini biliyorsan, word'lerin nereye gittiğini biliyorsun, onu söylüyoruz. Ya bunların grup teoretik şeylerine girmiyoruz. Hani oraya girsek herhalde, yani kitapta da yapmıyor bunu zaten de, hani o 3-4 saat gider. Hani burada aslında bayağı iş var yani, hani şey değil. Bizde belki yani graduate şeyde yapılıyor mu bilmiyorum, grup teoride de. Grup teori belki elektif kurslarda yapılıyor olabilir. So you saw it over there? Okay. Okay. Group presentation. Well, using free groups, we can give presentations of groups. Let me explain what I mean by a presentation of a group. So let G be any group with generating set B. So this is a generating set for the group. In this case, we write the following. G is generated by B. So this notation means that this set B is a set of generators for the group G. In other words, every element of G is a product of this G alphas. For example, let's, for example, consider the following group. So integers with addition operation. We may, for example, take B as this set, or we may choose B to be this one, or even we can choose B to be the set 2, 3. Okay, so each of these sets is a set of generators for this group of integers. Okay. All right. So all right. Now let me pass to another consideration. So let A be an alphabet. So consisting of letters like this, and F be the free group, on A. Then we know that then so then for any group G with generating set let's say B, generating seti şöyle olsun. Yani aynı indeks setin elemanlarıyla indekslensinler. There is a unique homomorphism phi from F to G, sending the letter X alpha to the group element G alpha for every alpha in the index set. Okay. Well, since this is a generating set for the group, this map is onto. Okay. Since B is a generating set, for G, the homomorphism okay. The homomorphism phi from F to G is onto. Therefore, we can write the following. Hence, G, which is equal to image of phi, but we know that this is isomorphic to F divided by kernel of phi. Okay. And in this case, we will write the following. So G is generated. So G is isomorphic actually to the following, or G is. So this will be a presentation for G. So X alphas are the generators, and elements of the kernel are called relations. So these will be called generators, and this will be the elements of the kernel will be called relations. Okay. So G is isomorphic to the following. It's generated by the elements of the free group modulo the elements of the free group, which lies in the kernel of the homomorphism phi. Okay. For example, so we can write Z as follows. Z is generated by one element. Let's say, yok şöyle yazayım, X diye yazayım. One element, and there is no relation. Okay, no relation. Here, F, I take F, the free group on the set A, which is just the one element set consisting of X, and homomorphism from F to Z is the following. Let's say, let's just send X to 1, okay? Then this map is onto, but not just onto, it's then actually isomorphism, and kernel of phi is just the identity element or empty word. Therefore, this is an isomorphism. So there is nothing in the kernel, empty word. Therefore, we can write it like this. Of course, we could use different generating sets for the group of integers. Then we would get different group presentations. So that's one presentation for the group of integers. Another one could be as follows. Mesela şöyle de bir şey yapabilirdik. Mesela yine G'yi Z alalım. A'yı X ve Y alayım. F free group on A. Free group on the alphabet A. And let's define, let's take the generating set to be the following. 2 and 3, okay? And let's define this map from F to G, which is Z, such that X is sent to the element 2 and Y is sent to the element 3. In this case, so what will be the what will be the kernel? Okay, so x küp eksi y kare galiba, değil mi? O kernel'da olurdu. Değil mi? So x cubed and y to the power minus 2 is what? So this is just x times x times x. So it is just, okay, şöyle yazayım isterseniz. X, x, x, y inverse, y inverse. So image of x is just 2, 2, 2, minus 3, minus 3. So this is just 0. Therefore, this element is in the kernel. And probably it is, of course, so kernel is the, contains this element, but it is not just that element. Actually, kernel is a normal subgroup, so it should be the normalizer of this. So normalizer of x cubed y to the power in f. Okay. Bunu ama biz şöyle yazacağız. So z, which is g, and that's equal to image of phi, and that is isomorphic to the following. So this is, of course, f divided by kernel phi, and we will write it this way. So f is generated by two elements, x and y, and kernel has, of course, you know, not just this element, any actually element in the normalizer of this element, but we will simply write the following. So we will write this, meaning that this is the group, free group generated by x and y, divided by the normalizer of this element. So that will be the actually notation. So when I write like this, this element is considered to be identity, but since this is identity, it will be identity in the quotient. Any actually conjugate of this will be also identity element in the quotient. Okay. Başka relation yok değil mi? Yani şey olarak evet, tek relation yetiyor burada zaten. Şöyle bir örnek yapalım. Mesela grubumuzu cyclic group of order 5 alayım. Yani mesela Z5 alalım. Z5 under addition. Bunu nasıl ifade edebiliriz? Bunu şöyle ifade edebiliriz. Yani benzer bir notasyonla. Bu tek bir eleman tarafından generate ediliyor. Mesela. Değil mi? Öyle ki 5. kuvveti identity. Yani bunu 1'e gönderdiğimizi düşünelim. O zaman şöyle yazmam yeterli olacak. Okay? So here F is again the free group on X. Let me write it this way. Free group on X. And the homomorphism we take from F to Z5 is the map sending X to this generator to 1. And the kernel, of course, just X to the power 5. Of course, this is isomorphic to actually set of integers, and phi is you may take phi to be this map. Okay. So group presentation is something very useful to work with groups, especially if you are doing algebraic topology. So it gives you a way of handling groups. How can we write down a presentation for the group, let's say Z cross Z, abelian group of rank 2, right? This is abelian group of rank 2. Well, we can write the following relation. I'm sorry, presentation. So it has two generators, let's say X and Y. Okay, two generators, but this is an abelian group, right? Abelian group. Therefore, these two generators should commute. Therefore, the relation I will write is just this. Okay. So generated by two elements which commute. So in this case, actually, this is my alphabet. F is the free group generated by X and Y. So no relation. And I take phi from F to G, sending X to 1, 0 and Y to 0, 1. Okay. Then you can check that this element is in the kernel, actually. And this gives a presentation for the group Z plus Z. Burada tabii yani bu şey demek değil. Yani kernel sadece bundan oluşmuyor. Bunun normalizer'ı, değil mi? So kernel of this homomorphism is the normalizer of this. So it is actually the commutator subgroup, right? This kernel of phi is just the commutator subgroup. Şöyle yazıyoruz değil mi? Commutator'ı FF. The commutator. It is the normalizer of this subgroup. Okay. Daha ilginç bir şey yapalım. Okay. Symmetry group of an equilateral triangle. Okay, let's draw an equilateral triangle. If I label the corners as A, B, C, then any permutation of these three letters corresponds to an to a symmetry of the triangle, and actually those symmetries are reflections and rotations. We have this rotation, let me denote by sigma. So sigma is the rotation, what kind of rotation? So this is counterclockwise rotation, right? And in terms of corners, that corresponds to the following permutation. So A is mapped to B, B is mapped to C, and C is mapped to back to A, right? So sigma is this permutation. What about, for example, sigma squared? So this is, you may also consider this as just 2 pi over 3 radian, right? Counterclockwise rotation. And 120 derece rotasyon. So its square is just, you apply rotation 2 times. First, A was mapped to B. If you apply it again, then A will be, B will be mapped to C. Therefore, A is mapped to C, and C is mapped to first A and then B. And of course, B is mapped to C and then A. So sigma squared is this permutation. And we have also reflections with respect to you know, heights with respect to each edge. So şu şey çizersek, buradaki mesela reflection nedir? Şöyle yapayım. Şöyle bir reflection'ımız var. Tau diyeyim. So reflection with respect to this line. So that corresponds to what? That corresponds to the corner C, right? Doesn't move, but A and B are just interchanged. So tau is just the permutation AB. Of course, tau squared is identity. And we have 2 more actually reflections. Another one is this one, and another one is the reflection with respect to this line. And those reflections, for example, this reflection will correspond to what? A is fixed, B and C are interchanged, and the third reflection is B is fixed, A and C are interchanged. So you see that we have all 6 permutations are listed here, including the identity permutation. So symmetric group of equilateral triangle is isomorphic to the symmetric group on 3 letters A, B, C. Okay. Şöyle yapayım. Şöyle yazabiliriz. So our symmetric group G of the triangle consists of identity element and then the permutation ABC, ACB, AB, BC, and AC. So this is just the group on 3 letters, which is just S3. I can also write it this way. I can list the elements, using this notation. So I have identity permutation. I have sigma. Sigma is just the ABC. I have sigma squared, and then I have tau, and then I have conjugates of tau. For example, sigma tau, sigma inverse, and sigma squared tau. İsterseniz şey yapayım, hatırlatayım. Sigma şuydu, ABC'ydi. Tau da AB'ydi. Mesela şu conjugation neye denk gelecek? ABC, AB, inverse of this is just, of course, actually sigma squared. Değil mi? Çünkü kübü identity bunun. Bu da neydi? ACB. Dolayısıyla ACB. O halde nedir bu? Bakalım. A is mapped to C and C is mapped to A. Therefore, A is mapped to A. What about B? B is mapped to A is mapped to B, and B is mapped to C. So B is mapped to C. Of course, we just write this as BC. So conjugate of AB with this element is just BC. And similarly, so this is BC, and this will be just AC. Okay, you can check that. We can write G also like this. So this is just generated by 2 elements. Okay, let me say this is X and this is Y. I can write it this way. X and Y. so that so X will be mapped actually belki şöyle diyeyim. Let me consider the free group generated by X and Y. X and Y. So this is the free group. And then we have the map from F to G, so that X is mapped to sigma and Y is mapped to tau. Then G will be the following. G will have the following presentation. It's generated by X and Y, so that X cubed is identity, right? This is in the kernel. Y squared is identity because this is an involution, right? Its square is also trivial. And we have one more relation. What is that? It is the following: Yx, Y inverse, and then X. So what we mean is the following: tau, sigma, tau, or tau inverse. This is the same as tau times sigma is just identity element. This is really the case. We can check. Yani işte isterseniz yazalım. Şimdi AB, ABC, tau inverse, o da AB. Sonra yine ABC. Bunun identity olması lazım. Bakalım. A is mapped to B. B is mapped to A. A is mapped to B. And B is mapped to A. So A is mapped to A. What about B? B is mapped to C. And then C is mapped to A. Bir dakika. Yanlış mı yazdım? Bir saniye bir kontrol edeyim. X square. Şimdi pardon, B ile başladım. B C'ye gitti. C A'ya gitti. A da B'ye gitti. Dolayısıyla B B'ye gitti. Tamam. O zaman C de C'ye gidecek. So this is identity element. Okay? Identity element. And G has this presentation. Okay? So the free group on 3 letters has, of course, several presentations, but this is one of them. Okay? It has 2 elements. One of them has order 3. The other one has order 2. And these 2 generators also satisfy this relation. It is not the commutator relation, but similar to commutator, but it's not the commutator. Evet. Ara verelim isterseniz, aradan sonra devam ederiz. Nerede? Şey kaydı. Dur. Okay.